It's just out to coffee with some until so I'm sorry if I come in.
Oh, no, not at all.
Yeah. But do you have to like simulation?
My partner's cousin
Wouldn't get it. That's content for it.
Yeah.
Indeed.
It will be nice.
Like people really hate that.
Oh,
I mean, we have structure on all of them. So people hate that much better than that.
Do you need water or anything? Or-
Oh, maybe I'll get a glass of water.
so I look at the research papers that I
It might be from what people
use for literature review and see what they did. Qualitative applications. Oh, yeah, I see here, right? Is not
They're coming back.
government,
Yeah.
economic design, so they have some policy applications. But I'm not too worried about that. Oh, you're free.
I don't know. Ali.
Oh, it's Ollie.
Ali's your son.
Good, how are you? Not really, I was working on my thesis.
All right. Hello, everybody. Welcome to our first talk in the second half of the term. Today, we're very lucky to have. Can we get this up any higher? Okay, so it will be down here. Great. Okay, we're very lucky to have Ana-Andreea Stoica, who is a research group leader in social foundations of computation at Max Planck in Tübingen. So before she was at Columbia University, where she did her PhD. There's a lot of things that we care about here around efficiency and social objectives in machine learning with AI, using tools that we use a lot, unsupervised learning, game theory, behavioral modeling, focus on thinking about helping people gain access to information and opportunities. So let's listen to what she has to say. I'm very excited.
Thank you all for the nice introduction. Thank you all for being here right after Easter also. I hope you can see well. This is the first time I feel so tall compared to the screen, so I'll point to it well. Yeah, as you mentioned, I've been at Max Planck for about 3 years now. I work on a variety of topics at the intersection of network science, economics, unsupervised learning, and I care about how we apply AI tools in platforms in particular. In particular, I care about how algorithms that we deploy on platforms reshape our personal networks, the markets that we interact with, such as job markets or service markets, and the content that we get from platforms as well. And there's a big hope that if we design these algorithms well, then we can get better access to opportunities, such as new jobs, to resources, such as information, or new relevant connections for us. And overall, we can improve our welfare and become a little bit more prosperous in general. At least this is the hype that a lot of people are very excited about in applying AI tools in these digital platforms as well. There's many challenges with this view, and some of them that that we will tackle today are related to how algorithms that we deploy can also reinforce inequalities between different demographic groups in society by reinforcing social inequalities that we see as well. One of the biggest challenges is especially when we deploy algorithms to connect people with resources. And to give you an example from some years ago, a very widespread algorithm was deployed in the medical system to connect people with the right diagnosis. And it reinforced racial bias between demographic groups, between Black and white patients, by saying that white people needed more medical needs than Black patients, although they had a similar level of symptoms or the same kind of systems, similar level of need, in fact. And it wasn't because the algorithm in itself had some bad intention or some bad intentional design, but it was because it was using healthcare costs as a proxy for need. And this is associated with social inequality between different demographic groups as well. So this is an example where an economic externality affected the ability of an algorithm to predict well and to be accurate with how it with individual needs across different groups as well. The reason for which this is a particular large challenge is because we have social, economic, and algorithmic objectives interact, and this is where my work comes in to disentangle factors from each of these fields in order to make the algorithms that we deploy more beneficial for people in general. So a common feedback loop that you would often see in these settings is that, well, people have incentives and that shapes their behavior, how we act online, how we connect, how we interact with the content that's given to us. And that can create feedback loops that get fed into the algorithms we deploy that will affect our future behavior as well. And if there's social inequality or equity issues that we notice, this can get entrenched and particularly amplified when we deploy these algorithms at scale. So even small biases that we see can turn into very structural ones in large digital platforms. In order to disentangle these factors, I combine methods from different fields together, from statistics and machine learning, economics, and algorithms. So a lot of my work sits at the intersection of these fields by blending in theories and empirical studies in these domains. In order to do that, the purpose of using these fields is to build optimization functions that balance social and performance objectives, such as fairness, equity to different demographic groups, as well as accuracy or predictive power, and to equip these optimization problems with elements from economics, such as like incentives, market elements, and to make them robust to externalities or strategic behaviors. And finally, to solve these complex optimization problems with new algorithms that are able to be both scalable and have some optimal guarantees as well. So today I want to talk to you a little bit about one example of such work that blends techniques from these fields that is focused on causal inference from competing treatments. I'll explain what it means, but it essentially will blend techniques from both causal inference, a bit of data science, and game theory applied on a digital platform problem. And we presented this at ICML last year. It's joint work with people from our lab, Vivian Naslik, who's a PhD student in our social foundation group, and Moritz Hart, who's the director of the Institute and of our group. So to tell you a little bit about, I don't know how many people are familiar with causal inference, so we'll go in a little bit of detail of what it means. But many of you may have heard of randomized controlled trials. This is a common experimental design to estimate a causal effect in many different domains. Most prominently, it's used in development economics in the last decade or so to assess the impact of a particular policy. Is it effective to give people subsidies or cash versus in-kind transfer? And the way that is done is by selecting a small group of people, running a randomized controlled trial where some people get it, some people don't, and estimating the effect of this particular intervention to see if, for example, their welfare increase or some other output. It became really the gold standard in the field for policy assessment, as the number of RCTs have like skyrocketed in the last, I guess 20 years or so. and in a particular impact in the global south, with the number of RCTs increasing a lot in Africa, in South Asia, in Central and East Asia as well. And even since 20 years ago, people from development economics have pointed out that it's not easy to run these experiments, but they're very prevalent. And they're also prevalent in many other fields, such as in medicine, where you might have heard in how we design a new medical treatment and estimate their effect. And in marketing as well, knowing whether a particular campaign is successful, such as in online advertising or other digital problems. Some of the one challenge that I will focus on today is when there's multiple experimenters who are running concurrent experiments on the same population as well. And this is a problem that people have noticed even in development economics from 20 years ago, because when running in an RCT for assessing the effect of a particular policy was done on the same set of people over and over again. And as Duflo had mentioned in one of the reports that, well, this can become problematic because the population gets affected by staying and being exposed to sequential treatments. And that can affect, well, the external validity of the experiment. It doesn't mean that what you estimate is no longer a good quantity statistically, but it's no longer relevant for the general population in which you're trying to make a causal claim as well. Now, this is a problem not only in economics that was observed, but it's prevalent in digital platforms as well. Such RCTs come in the form of A/B testing in online platforms, for example, for testing new algorithmic features, where a set of users would see one type of content A, a different set would see content B. You might have been exposed to many of these, some of them you notice. And the purpose is to estimate which feature appeals to you more. Of course, big companies use like a ton of these experiments every year, more than 10,000 a year from each Google or Meta. And they have social impact as well. So they're not all about running, what kind of product might work well for you, but some of them have particular social applications, such as learning what kind of intervention in terms of an information campaign appeals to people better in terms of learning about COVID-19 or other healthcare related information. So a very large set of RCTs were run during COVID-19 by Meta, on the order of like hundreds to 1,000, to learn how to best target people with information about where to get healthcare and information about the COVID-19 vaccines and the disease as well. The goal of these kind of experiments, as I mentioned before, is to estimate, I hope you can see these corners too, a causal effect. Is this an effective intervention or not, by learning the treatment effect between our A/B tests, A and B groups as well. And based on that, the purpose is to decide deployment at a large scale, right? So if we get a good intervention, if we get a good treatment effect, then we can decide to run this campaign at large as well. Now, the same but slightly different problem that we saw before is that in digital platforms as well, people are subjected to multiple experiments or multiple ad campaigns at the same time, right? So when you go on, let's say, Google search, you see a set of ads. Each of them may be emblematic of a A/B test run on you as well. And therefore, each of them you can think of as competing for your attention, and therefore the positioning on the web page in which you see these different campaigns will affect your response. One effect is we know that people's attention decays as we go further down on a page. There might also be interfering effects. If you see an anti-vaccination campaign first and then a vaccine campaign, that may affect the way you respond as well. So we care about how the different experimenters can compete for your attention, and to understand how we disentangle the causal effect that one would like to estimate in this realm as well. What we do here is we model this competition for a user's attention by understanding how positioning works and blending techniques from game theory for modeling competition among different experimenters in order to disentangle the causal effect that we statistically want to estimate as well. So at a high level, we model this competition among different experimenters using an auction design. Each of them is running let's say, an information campaign, which is doing an A/B test, and they're bidding on subjects. Through their bids, they get to show their ad further up or further down on a page. So if you bid more, maybe you get to show your ad further up, and hoping that would actually help getting a better effect as well. So under this, you get a particular data distribution of the people who will click or not click on your information campaign. And your hope is you can use that data effectively to estimate a causal effect. Now, in causal inference, we'll go in a couple of details of how that works too. The purpose is to understand the effect between the treatment and control. And we don't really know how to do that, perfectly. What we can do is to minimize the estimated error from the data that we get under this competitive process. Generally, in causal inference, we have statistical tools to estimate this. If we have a good experimental design, we have randomization, and that gives us good statistical conditions for estimation. The difficulty here is that this is an endogenous process where every time an experimenter changes, for example, their behavior, that changes everyone's data distribution. So it's an ever-moving quantity that we need to estimate as well. So the main result here is that, we care about what's the equilibrium state. And at equilibrium, we can get an optimal strategy on what's the best data to get from the perspective of the experimenters and how to estimate a causal effect for that particular data, right? This means, where are we? Yes. So generally in equilibrium means that I don't want to deviate from my strategy. I'm doing the best I can given full information I know about everyone else, and I can use both my behavior, everyone else's, in order to estimate a treatment effect. If there's questions also in the middle, please do ask. So let's go with our running. We're going to see exactly how this works, and so far it's been a bit abstract, but let's go with our running examples of running an online campaign in the form of a randomized controlled trial. What would the user see if they go on a web page? As I mentioned, maybe there's different ads. Each of them is some information campaign run by a different company that is doing an A/B test, right? So the ad is a treatment, could be version A versus version B. And multiple experimenters compete for the user's attention by trying to fill up the slots for experiments. And the behavioral part is that, an ad will affect subsequent ads' outcome. What we know experimentally is that, for example, users' click-through rates really, really go up if they see content further up on the page. And it goes down as people go down on the page because their attention decays or they already found relevant content and so on. So what we care about estimating here is to say, what would have been the effect had my ad, my treatment, been shown first? And we'll explain why that is an important quantity. From the perspective of one experimenter, I'm one data science company running an A/B test. I want to know why I might get a low treatment effect. And I could have two answers. One, I just have a bad design. My information campaign didn't appeal to anyone, nobody cared about it, that's it. Or I got a very low position. And because I got buried under 10 other campaigns, nobody clicked on it. But they would have clicked if they had seen it first. So this is, in a sense, a counterfactual question. And I want to estimate that counterfactual. Had I been first, would you have clicked on it? Would you have thought this is a good campaign to run? And if I can estimate that question, then I know what to do. I know whether to invest in getting data and deploying my campaign, that's it. Or I know that my campaign was bad, nobody clicked on it, even if they saw it first, and I have to redesign the whole thing. So I know how to invest my resources in the next step, in the future campaigns that I will run. So this motivates this question of what would have been the effect had my treatment been first. And in causal inference, this can be quantified by the average treatment effect. The counterfactual one had I only been shown first. So maybe with a bit of notation here, I don't know if people are familiar with generally estimating treatment effects. but we can go through it. This is a ground truth. This is the ground truth we want to estimate. And it's fundamentally hard because, well, I want to estimate the average difference between treatment, this is version A of my campaign, and control, B, version B, of a quantity, which is the outcome of a user, for example, the click-through rate. And I want to do that on average for all users. But the fundamental problem in causal inference is that I only observe either treatment or control for each of them. I don't observe both of them at the same time, right? And that's why this is a counterfactual estimate. And in general, what I can do is to say, okay, I'm going to define it. I'm going to collect data. And under proper experimental design, I can estimate this quantity. And I can get some statistical guarantees for how close I can estimate it based on information theory, my design, and the data that I collect. It's kind of a double counterfactual because I'm also saying, well, I want this if I had, if my user had seen my treatment first. This is called a do intervention to say like, had I actually shown my treatment first? I haven't shown my treatment first for all users, but had I done it, what would have happened then? What would my effect have been? This is clear for people, right? Yeah. So this is called the average treatment effect for the first positioning, essentially. And because I don't have access to the ground truth, though, what I can is just like collect data from people. And if I were the only person in the world to run a treatment on these people, then I would have a much easier time. I would just estimate the regular quantity, the regular average treatment effect. And what we know about this is that, well, we can actually estimate this pretty well in a good experimental design. How do we do it? Well, we define a loss function between our ground truth and the data that we actually get. And a common loss function is the mean squared loss, where tau is our unknown quantity. The samples we draw from some distribution of users, and we use an estimator, tau hat, which hopefully gives us a good error from the ground truth. So the purpose is to minimize this error. And if I'm the only person in the world running a treatment, then I know that in general, under a good design, this scales more or less as 1 over the number of samples, right? This is where the power of experiment, the experimental power that sometimes you see, and you need a lot of samples because, well, the more samples you have, the less error of estimation you get. In our case, this is a little bit more complicated. It's not that I need a lot of samples necessarily, but I need good samples. So if I'm an experimenter, I could be a naive experimenter who, let's say I have a budget and I get to bid on users. So I could have an easy option to say, let me just bid on a few users and get my ads shown first. This is great because nobody has interfered so far with my data. Or I could actually spend my money, spend less on more users, but then my ad gets to shown further down on the page, their attention decreases, so I get more samples, but each of them maybe has more error to it. Of course, this embeds an assumption that lower ranked samples have a lower effect. So we know that as people go down through a web page, their attention would decrease, the click-through rate decreases, and we do know how to estimate that. We also know that actually if you go on, say, Google, they publish the click-through rate decrease for a bunch of domains from science and technology, fashion, ads, and so on. So we know and we can estimate this separately. And if we know these discount factors, for example, my campaign on shown third gets like 3 times less clicks than first one. Let's say I know this once as a parametric model, then I can say, okay, I can get more data, and I can then use that data smartly in order to recover the effect at first position, right? So I know if I got 2 clicks on position 3, I would have gotten 6 at position 1. So I can use some inverse propensity sampling to recover my effect as well. This is still a hard problem, though, because now I don't know what's still the best data to get. So as I bid on subjects, right, I would get some data distribution. The moment I change my bid or someone else changes the bid, the whole data distribution changes. And therefore, the value of information I get for that data also changes. That's why now the problem that we have is a little bit more complicated, because now I'm minimizing the mean squared error between the ground truth and the data that I get. But the data that I get comes from this endogenous process that changes every time someone changes a bit. So I have a joint optimization problem between making sure I get good data. This is one of the levers I can pull. And second, once I get data, how do I use it for proper estimation? Right? Use my estimator choices in order to minimize my square root. And I have to pull this lever simultaneously, which is why it's a bit more difficult joint optimization problem. As we mentioned before, it's not impossible because once I know I have some data, I can actually recover my effect by discounting it, each sample properly, right? There's still the question of what is the best data that I could possibly get in order to minimize this quantity.
But on the issue of discounting, it seems like you're assuming some structure about the discounting.
That's right. The only structure we're assuming is that there's some parametric model in which the effect at position R is some fraction of the effect at position 1. I don't need any other assumption on it.
And is this post specific, like campaign specific, this fraction? Because I can imagine there are going to be campaigns where you don't have an image.
Yeah.
If it's top position, then it really matters and there's a huge discount.
Yes,
Have, like,
it is campaign specific. That's right. So what you can do here is to say, I will run a pilot experiment to estimate these separately, or I use estimates that are given to me by the platform. For example, Google gives you these. So if I say I want to run an information technology campaign, then I already know that Google every year publishes these alpha R's discount campaigns. They tell me what it is. And they differ in information technology versus fashion versus other ones, but they do publish them. Yeah. But we don't know if they're like the best estimate I could possibly get, but that's a different question. We can discuss that. All right. So how do we solve this problem? Essentially, our solution here. Our solution here is to give you an equilibrium solution and to tell you, well, approximately under some option systems and under some statistical conditions, we can solve this and tell you what's the best strategy. Maybe I'll get a little bit into like how this data distribution actually gets formulated in order to get some intuition for what the user would do. So what actually happens in our problem? I have a bunch of experimenters. Each of them is running some RCT, some information campaign. Imagine I have like, I don't know, Google and Meta and so on, each of them running. And they go under a bidding process to get a set of users and the position at which they get to show their ad. So for example, experiment the yellow one got to show their ad at position 1 for a user, 3 for another one, 3, nothing here, and then 2, right? This comes from a bidding process where at equilibrium, for example, at a Nash equilibrium under an auction system, I would get this data distribution. Now that I have this data, the second part is for each experimenter to run their own RCT. So what do? Well, they get to show either treatment or control for each of them. And this is the collected data that they actually get. So they collect the position at which they shown their campaign, the actual outcome, for example, a click-through rate, which is in the variable y, and whether it's treatment or control. Under randomization and independence of sampling of users, I get to identify the effect. So all I need is to collect this data and find a good estimator in order to minimize the treatment effect. I still have to optimize how to best use this data, right? So I mentioned that if I know by how much I discount the click-through rate or the treatment effect actually at each position, I can use it smartly. But I still have to do that. So these are the two levers that I'm pulling. On the one hand, I'm bidding for data. And on the second one, I'm using that data smartly in order to estimate my treatment effect. So doing that jointly is difficult, But what we can prove is that, well, it actually no longer it no longer grows with the number of samples, but just the number of samples at each position are discounted by the decay in treatment effect squared. The squared here comes from like the variance increase, which provides us with the square. And you can think of this as, in a sense, the informational value of that data. It's not that each sample is equal, but each sample is now discounted by, well, where exactly I show in my ad. This comes from an information theory argument, such as like a lower bound that is given by Lequin's theorem. And it's actually tight because we can find estimators that gives us this particular bound. Why? Because, well, I can discount the samples at each rank appropriately, and therefore I can get this quantity to be tight. It's still hard because now, well, what do? I have to optimize this data distribution through my bidding. So I could get fewer samples, so a high number of samples at rank 1, but each of them is great. Or I could get more samples, but each of them is discounted by maybe a lot, maybe a little bit. What is the optimal combination of these samples is the question that we're looking at. So each of my bidding strategies, or the way that I bid for data, will give me a different value. What is the optimal one? What should I do as an experimenter to get the best data that I could? This is kind of hard also because I'm essentially trying to optimize 1 over some random value. Well, the random variable comes from some auction. And it's hard. And what we can do is to show that, well, I don't have to do this complicated procedure. I can just optimize for the expected value, the sample value, and I can do that by finding the Nash equilibrium of a game. So where the game is, well, I bid for data, everyone bids as well, and at equilibrium, that is the best solution that I could possibly get. I don't want to deviate from it. This just means that my utility function is the expected value of the data itself. Right, so this is the value that everyone is maximizing independently. And I want to show you just a little bit about how this game looks like, what's in equilibrium, and yeah.
I can't help but think that depending on the outcome you're interested in, this discount function might even like not follow this pattern of constantly increasing. Like if you're like looking to buy glasses as a consumer, you don't want to stop at the first ad you see, so because you want to like search the market a little bit until you figure out what's the glasses that are going to fit you. If you're looking for like specific good, the ad has to optimally be relatively early, but not too early in order.
Oh, not too early. I see.
And that's already an example where the attention returns are not monotonically.
Oh, I see what you mean. That's right.
And like, it's about public opinion. It might even be that you have to. It's weighing on user if you're the last word in the user's mind. So it seems like there are some.
Yes.
So what are these settings where it's obvious that this function?
Yes, I can tell you about some of those settings. So the first point is that's right. You don't need this monotonic decrease in attention. You also don't need it for the results. The results only would hold essentially with the same guarantees for any shape of these. The only thing that the results are contingent upon is monotonic decrease. And what is the closed form of the equilibrium? So what is exactly everyone's strategy that I will show later on. Now, empirically, for example, it didn't make it into the paper, but we ran experiments on Google Ads of trying to promote our PhD program in computer science, right? So we are within like computer science research on for these campaigns, and we estimated these effects. They're very steep in this one. They're also very steep from what I've seen in what Google publishes in large industry domains. So again, like fashion, technology, research and computing, things like that. In all of these, we've seen like deeply decreasing points. One in which is not is a very funny example that's less related to digital ads, but rather to people's like attention on or what they perceive jokes to be funny or not. So when they see like, maybe you know this New Yorker caption contest, they have an open data set and people vote. There's an image, there's different captions for it, and people vote on the funniest caption. And of course, the order in which people see captions really matters. This is an open data set you can play around with, and it's really nice to look at because for some captions, most of the captions, you see that the first answers have a high effect of being found funny. Because if you see something very similar later on, you're like, well, I already saw it, it's no longer funny. But later on, for some particular subset of captions, really hard to identify why, the funny answers are later on, actually, as people like learn to understand maybe it's a difficult image or a difficult caption and so on. So that's one example where we saw that people found it a bit funnier later on rather than on the first answer that they saw. In digital ads or like digital campaigns, I haven't seen this effect so far, but there must be cases in which what you're saying is true. Yeah.
Because I do believe that like this function is going to be monotonically decreasing. Like if the outcome is being in the consideration set, like your ad that you click through being in the consideration set.
Yeah.
But then like I could imagine you're looking at different social media platforms where people just see a product and they can buy it right away, where you might already not see this like strict monotonicity because they're like
yeah.
I think the first like face screen is not going to be the thing.
That's true. We haven't looked at other platforms with other designs that may induce these effects too. We've only looked at essentially this sequence of campaigns. Yeah.
I was just wondering, how do you account for, especially with information? Because I mean, if somebody's already essentially looking for information that they already agree with, then they may be willing to search further down. Are you able to?
Yeah. We don't account for it here because we don't assume anything about these facts. They can be anything. So from the experimenter's point of view, maybe they have to do that by saying like, oh, I need to account for this when I actually estimate these effects. I think this gets treated differently. So if you go on Google Advertising, they provide you with a framework to estimate these, for example, on different domains. How they do it and how they account for this confirmation bias might depend a lot on the domain itself. But in this case, you don't have to do it just because this is some constant. I don't mind what it is itself.
Just thinking about your example, COVID, vaccine.
Yeah.
There's a lot of confirmation about.
Absolutely. Yeah, I think people in recommender systems, so this kind of model with position bias is very common in recommender systems. And I think one way to do it there that I have seen is that you fit a latent preference model to a user. You kind of know their preferences, and therefore when they go on a platform and they see sequential content, essentially you try to understand how their preference model interacts with it. So the position bias relates a lot to your preference. If I have a very high anti-vax preference, then probably that changes a lot the effect that I see depending on the sentiment on each piece of content. Yeah. But I think it's a great question. Cool. So the main idea here is that now what changed from being the only experimenter in the world to having multiple people is that I have to undergo some competitive process to get data and to optimally use that data for my effect. And the question, well, why is this a hard optimal value to know is that, well, should I get less data, but each of them is like really good, a very good data point with low error, or more data where each data point comes with higher error margin that I have to account for? So the answer to that is basically I can know what's the equilibrium and what's the best data distribution to get as a solution to this game that we're playing, where the utility of each player is to just maximize the informational value of the data, right? The sample value that I have. So, yeah.
Maybe you can tell me what to think about why we would want to look at like a pure Nash equilibrium here, because like usually in experimental design, like mini-max solutions, not pure strategy.
Yeah. You don't have to. It just so happens that in this game, for example, in a large set of auction systems that we looked at, you do get a pure Nash equilibrium where if you have to bid at least a constant amount. So for example, in digital campaigns, you can't bid under like a cent or some small amount of value. And under that framework, you do get a pure Nash. If you don't have that, the settings in which you don't get a pure Nash equilibrium is the setting where you can just bid any fractional amount. Then there's no pure equilibrium, and you would look at mixed ones too. Yeah. We haven't looked at how those looks like, so we only look at the pure ones because they told us something about the strategy itself. All right, so let's see how this game looks like, perhaps. So we can spend a few minutes just like seeing what a game is like and what an equilibrium would look like. I have several experimenters, and they bid on subjects, right? This bidding is essentially some matrix of subjects and experimenters. Everyone has some budget, and they have to use what's called. They can't use like all fractional amounts. They have to use at least 1 cent, let's say, per dollar value. So each experimenter is going to use their budget to bid on people. And an auction is characterized by some allocation rules that maps my bid to some positioning in which I get to show my ad. Right? One way to see, and there's many types of auctions. Maybe you've seen in advertising, there's first price, second price auctions, and so on. In digital media and in recommender systems, you also see other types of auctions. For example, one that is slightly randomized. So for each subject, for each user, you can choose a random ordering of the experimenters, and each experimenter will try to win that user with some probability that depends on some relevance parameter. Am I in the right segment of the market? And the bid that one experimenter A has placed at each time step. So this is a type of auction design that was influenced, or that was proposed in the past. It's also from an ICML paper on recommender content and recommendation content design. And for this allocation rule, essentially, everyone, and under some bid, they get this allocation that we've seen before, where every experimenter gets some positioning of the ads. So, and that gives you a sample profile. So for example, we looked in the past at experimenter yellow, we got like 2 samples at rank 1 at rank 2, and so on. So now this creates the value of the sample of the data that they can use for their experiment as well. So in the setup, we know that there is a pure Nash equilibrium. There's a unique one. And the equilibrium was interesting to us because, well, some parts were obvious. You should spend your whole budget, bid on everyone that you can, and minimize competition with each other. What wasn't obvious is that you can do that in 2 ways. You can either split your subjects by saying, well, I'm going to spend my budget on the first 2 users, and you spend your budget on the 3rd user, and we split our segment of the market. That wasn't the actual equilibrium, but the equilibrium was to still compete on common users, for example, on user 2, but to minimize the competition. So we're not all going to spend the money on the exact same users and leave some apart, but try to minimize competition as well. And of course, this might depend on the nature of your auction and the setup of your allocation function. But this type of result essentially, and for a large set of auction system, this would give you that this is approximately an optimal solution to your original problem, the estimation error game. And that hinges just on a concentration result to say that the sample value, the value of the data that I get, concentrates around its mean with high probability, which happens in any auction in which I have some positive probability of getting users at rank 1. This is the one that I've shown is one example of it that gives us this equilibrium. You might get a slightly different equilibrium if your decay factor is not monotonic. So if your strongest effect is at rank 2 versus rank 1, this would look slightly different. But this doesn't matter on what exactly the decay is, just that there is one. And this brings us to the point of like, okay, we have this platform experimentation, and there's many related methods that you might be interested in solving this. Off-policy methods give you these estimation guarantees, also using this inverse propensity sampling, using positioning, but it misses endogeneity. So here it gives you what's the optimal policy given a set of different strategies I have, Whereas the optimal solution we give tells you that, well, I have to let the system re-equilibrate based on everyone's behavior, and then I know what's the optimal policy, optimal estimation strategy to use. In digital advertising, you see a lot of AutoML methods too that learn optimal policy usually for one set of bidding systems. For example, in Google Ads, use second price or first price auctions more recently. And there's many other related problems that you might find interesting. So we looked at one in which different experimenters compete for the user's attention. Of course, there's a different problem at the level of the users, such as modeling interference. And there's a large body of work that thinks about how the user's spillover effects affect my ability to experiment when, well, I thought I gave you a version A treatment, but someone else talked to you, and now you're actually on the control group or vice versa. And this is a type of spillover effect you can model with different network models by understanding, well, how large is the spillover effect? This is my friends, friends of friends, and so on. And if I can contain that, I could recover my effect up to some guarantees. So a quick summary of the work is that we get this optimal estimation error under endogeneity by finding what the equilibrium is. And from there, I can find optimal estimation that finds this error. It's nice that the equilibrium is in closed form as a pure Nash. It doesn't have to be depending on the auction system that you have. And it answers this question. Should I get less data with better guarantees or more with each of them with worse estimates? Essentially, and it gives you what's the optimal solution for your data question. I can read more on our paper here too, and maybe I'll spend a couple of minutes on just telling you that this relates to essentially this is at the intersection of two domains that I'm particularly interested in. One is in policy design, one is in online platform design. So we motivated this question by being inspired by work in development economics, in which you have this competition of experimenters that run on the same population. Of course, you don't have this kind of like modeling setup, the bidding system in these kind of cases, but I do care about like how do you set up your experiment correctly in order to have external validity and to understand how do we actually test what are good policies for this kind of case as well. Other applications in platform design that I mentioned are of course related to recommender, ranking system that shows sequential content. The optimization problem that we looked at was this mean squared error problem specific to our causal inference case, but it doesn't have to be that. You can extend this to multiple different types of optimization problems for conditional treatment effect or other optimization problems as well. So these are some of the follow-ups that I'm personally interested in as well. Maybe I'll end up here to say just like this is kind of at this intersection of like game theory, statistics, and it relates a lot to how people interact with digital platforms. And then on this note, I wanted to use also a minute to tell you a little bit about one conference that is now in Germany, and it blends a lot of these questions and techniques that I mentioned. It's called EMO. So it's equity and access in algorithms, mechanisms, and optimization that we build with Redia Tablebeb, who's also in Tübingen at the university, and Irene Lau from Stanford. And we talk a lot together about this kind of questions on inequality, access to opportunities, how do we blend economic techniques, computational, from computer science, I guess, sociology, and also legal questions on policy design and regulation. And our next conference just opened up. Is going to be at LMU in Munich, so in Germany, which is why I'm telling you about it, because it's the first time it's being held in Europe and particularly in Germany. And the call for papers is out in a month, so you might be interested in learning more about this kind of topic, seeing our previous conferences as well. So I'll be there, but happy to chat more about any of these. Yeah, thank you all.
Great, so we have some time for questions.
Just a quick comment that URL is saying this connection is not part of it.
Oh, I will fix that. Okay. But you can also use this. This will take you to the general press. Yeah.
Yeah. And we are already given discount percentage by Google. I want to ask how much more accurate it is with defining a model.
Oh, I see. So you still need our model even if Google gives you these discount factors. Essentially, you need these discount factors. Doesn't matter how you get them. You can get them yourself by doing an estimation problem. You can get them through Google. But then you still have a problem. And the problem is that, well, what do I do with them? Do I use them to get some data? And maybe it's like less data, but each of them is like pretty good. Or do I get more data and I know that the discount factor would essentially like tell me how worse my data is. So essentially, if I know the discount factors, what I know is, let me show you this part. Where is it? Here. I know this quantity, right? But I don't know what's still the best strategy to get this quantity because I need to know what happens in equilibrium with everyone else. I know that I can change my strategy to optimize for this, but if I don't know what the equilibrium is, I don't know how that will affect everyone else's. And if someone else changes their strategy, that will affect me as well. So the reason you still need this model is because you need to know what happens under some equilibrium setup. Otherwise, you don't get any predictable and consistent estimate for your optimal error, even if you know these a priori. I hope this answers a bit of the question. Yeah.
How useful this would be for where they want to rank and like how much are they willing to pay more for a better ranking? How big it is to paying based on or rather than the brute force attempt, which is, I think the first result will definitely generate more. Like I want to understand how more fine-tuned this result.
I see. Yeah. The thing is, yes, and I think that's the right question to answer. Essentially, if I didn't know any of this, what would be the effect on me as a business? And the effect would be that I could have my naive strategy of just bidding maybe a lot on a few people, and I have no guarantee that that is any close to the optimal, to the true optimal error that I could have. It's a number, but I just don't know anything about it anymore. I lose the guarantee that that actually estimates something valid within my experimental setup. So I don't know, for example, if I got a low treatment effect, I don't know whether I got it because, well, some data got shown low or my treatment is bad, essentially. If you get to estimate the true sample value under some equilibrium, then what I do know is that I'm very close to the optimal one. And under that, I know that my low treatment effect means something about my sample. I know whether like, oh, I get a treatment effect of like 0.0 whatever, then I know it's because of my campaign. It's not because of the positioning. Whereas if I just do a naive strategy, I don't know which one it is. So I can keep like changing my campaign, but I will not know whether the effect is on my campaign or is because of the positioning. Whichever.
So it's somewhat related. It strikes me that it's related also to something else I mentioned before. It strikes me that there are going to be some goods for which what I care is not making an impression as a firm, but I care about being omnipresent. And for that, I might want to maximize reach, even though it's a low rank. It seems like it's hard to put structure on the problem in a way that you don't cook up the result for when companies would want to maximize reach rather than. But I wonder, like, if you thought about it.
Yes.
Like an obvious thing that is not super hooked up is if the good that you're trying to sell is a good with like large network externalities.
Yeah.
Like you're trying to tell people come on my platform because it's great. You don't want them just to open the click to the platform, but you want them to think that it's valuable to be on that platform. And if the platform is omnipresent, then people will want to. So like, this could be a story, but like
This is a good question, and I think to capture that, you would define a different estimate, essentially. If you say like my estimate is not what happens had I been first, but what happens if I'm just like present, right? If I'm a company that exists and people see a lot of coverage, then that defines it totally different. You don't need this condition. You have perhaps a different effect. You're trying to estimate the effect. You estimate the effect of like getting any rank at all on people. You see what I'm? Yeah.
I mean, one way of putting it is you're right. I mean, like, there's one thing is the outcome that you can measure within the campaign.
Yeah.
And the other thing is an outcome that you really care about, and it's not clear the intermediate outcome you can measure within the campaign, in which you're trying to measure. Streaming effects.
Yeah.
Are the ones that you ultimately care about. If you care about how much product you sell as a result of exposure to the campaign.
I see. Then you might need a different outcome, I guess, and to know whether you can measure that or not. Because there are downstream, like one outcome that I mentioned here is like click-through rate, but it's not the only one. Sometimes it's about more like conversion rates or like downstream effects too, and those are a bit sometimes confounded by other factors which we may not fully measure through this. That's true. That's what you mean?
Yes, but the context in which I raised this is like the theorem seems to make a strong statement about how you should target.
Yeah. And
what's less clear to me is that like it's not obvious depending on what strategies you have available that that's what you want to do. So to target people that are less exposed to other goods because like it's obviously more expensive. And also it's not clear that it's like depending on your objectives that that's what you actually do.
Yeah, this is only, you're right, the statements are hinge on knowing that this is your only goal.
Right.
If you have different goals, then you might have another pot of money that you invest in like market discovery on like completely other goals that you should run. This is essentially being like, I have a pot of money that I want to invest on a study, and this is the outcome of the study. If that's the only thing I care about, then that's the best thing I could do. But if I have a multi-objective thing where I care about how do I invest in like a small study versus a downstream effect versus a market discovery point, then I might do a different. This is a more high-level question of how I should invest all of that money and how I should balance these. Yeah, because maybe you could run a smaller study that is a bit less accurate, but then do something else with the rest of the money where I actually discover a new community or I do something else with it. Yeah. Yeah.
Could you comment a little bit on what is the role of AI at the moment in this bidding process, in the selection of ads? Just a little bit more on where's AI fitting into this?
Yeah, so I think a lot of bidding methods are based on like automated learning systems. That AutoML, for example, is one subset of research directions that are learning how to bid very well. And they tell you like they don't often give you like a very interpretable solution of what is the best thing to bid, and they're often constrained to saying like under this system and under this one auction I'm learning how to bid very well, but I don't know what that means exactly and whether that is something maybe more generalizable or gives me some guarantees that I know to generalize in other settings too. So I think there's the connection is to say like I could learn how to bid very well into one auction system, but I don't really know what it means. And this gives you more of the statistical foundations of like, I know what it means. If I know what it means, then I can also learn how to do it very well.
Yeah. So, I mean, I think this is still sort of following up on some of what you got. But I mean, one of the things which is interesting here is like your estimate here with the fact that this like do over the rank, you identify all the potential outcomes of a rank when you observe any rank. Because you know this structure.
That's true.
If you don't know this a priori, because this is the same thing about like why do you have a pure strategy here when like usually in experimentation the whole point is you don't, so you have to randomize so that you learn about this.
Yeah.
And the reason that you don't have to randomize over the rank is because you're not actually learning about this sort of like effect over the rank. So if you actually wanted to learn this jointly, which I think would kind of address this question you got, then you're going to have to do some kind of joint randomization.
Yeah, I see what you mean. So we tried this afterwards too. We said, okay, what happens if you have to learn the position at the rank at the same time that you're learning your effect? You have to split your data and actually like do this jointly, essentially.
Well, would you want to split the data? I don't. It seems like you might just be able to do this fully jointly. Same data.
Don't you have to split the data in order for that the estimate of your rank is, in a sense, separate from the estimate of your treatment effect?
You would have potential outcomes on two different variables. You'd be doing some kind of like a factorial structure. I guess you could call that splitting your data.
Yeah, I think that's what I mean with that. That's what yeah. So we've tried very, very like simple methods for that by just assuming they like also don't really have much error on your rank estimation when you randomize it. But then what we found at a high level is that it's not worth doing that. Actually, you don't get better error by learning the rank and doing the treatment effect, because then it just means you would have gotten better error by just targeting the first rank overall. So if you have to do it jointly, it's not worth it for your total error, at least in very basic settings. There might be settings in which you do, but yeah, in very simple ones, you kind of lose out. In a sense, in the setup that you mentioned, you kind of like lose out by doing this process jointly. It's, yeah, the samples that you gain after estimating the error on the second rank are not worth doing this procedure, essentially. Yeah.
So there's something completely different again. First of all, it wasn't your QR code; it was the preschool Wi-Fi that I changed. Secondly, I was really surprised by the direction that the talk went. I wonder if you could say more about this fundamental problem of the fact that some subjects are more likely to click on these things, and that what order they did the experiments in could affect outcomes, right? So I was expecting to be doing more about trying to seek unique students or making sure that the outcomes are independent. So is there other work on this kinds of?
Oh wait, so could you say the last part again?
So you don't want to make too much science on some inbred group of people that like clicking on random things on the screen.
Mm-hmm.
So I was more familiar and actually more concerned about it with the A/B testing that these companies do that's invisible, right? That you just get different versions of the app. It's not that there's something on the screen. So I don't know if that's been eliminated and everything has to be consensual now.
I see what you mean.
But either way,
Yeah.
you want to make sure that you aren't just getting some weird stuff on the people and saying that somehow represents the entire society, right?
Yeah.
So, and so this is nice if you're in this particular weird situation contending for page position.
Yeah.
but most of us are worried about whether or not our results are representative of the actual underlying population. So I was wondering, could you say something about that?
Yeah. Well, I guess in this case, do you mean that this should hold external validity beyond the design part, that this is like a page sequential thing?
Something different. It's not going off of what you're doing. I'm just asking related to your introductory slides. The related concerns. I don't see how this would relate to that. But maybe you do, and that would be.
I see. Let me think about what if I got it correctly in general or not. Well, there's different concerns that I care about in here downstream. This is one example of like how we should formulate this problem, but I guess further points that relate more is whether the way we use these RCTs are actually going to give people like a certain kind of resource further down. So for example, I am personally concerned of how RCTs are used at a very large scale for deciding on policies, and whether these policies are related to like giving subsidies, giving particular like opportunities, or connecting people with like job centers or employment centers. And these are at a much larger scale like used, and I care about whether we're doing it in a way that's like relevant for people and good in the way that we offer these resources. So this, maybe the connection here is related to like, in some cases we do these RCTs on digital platforms and the position matter when we give resources like information campaigns, which relates to this example of like, there was one case in which digital platforms that I saw were running all this like COVID healthcare information campaigns that were targeting people to like with how they should get to the closest healthcare center or what kind of information works best for them. But this is essentially taking the place of what a local government does and did also in real RCTs outside of digital platforms. So these are more concerned of like, should we be giving these resources in this particular setups, or like should we be using RCTs to give these resources, since oftentimes the way we target people can be confounded. We don't know whether it might relate to the general population or not, and also the sequential side of experiments can really affect things in the long run too.
So that was,
Yeah.
I appreciate your concern, and that's one I hope
Yeah.
that was, does this address that?
This will address that only in the particular setups where you care about not just random ads, but particular like informative ads. For example, if different companies want to target you with information, then this really relates to it, because they don't know whether their campaign is effective or not unless they run this properly on the digital platform. So if they run some random campaign on healthcare related information, they don't know whether it worked. They might say it worked, but they might say it didn't work, but it could have not worked because it got buried down because people saw something else. Does that answer it?
Yeah.
Okay.
Great.
Yeah, I can answer.
Any other questions before we close up?
Well, thank you very
Thank
much.
you.
And let's give you another round.
Thanks for the questions.